you take a look at a human hair, the cross-section of a human hair, that's about 100 microns in diameter. So these robots are small enough that you might be able to discern a little dot on your screen or finger if these robots are crawling on it, but you wouldn't be able to resolve their features. My name is Itai Cohen. I'm a physicist at Cornell University, and my lab is interested in microscopic robotics. One thing that has always been a vision for microscopic robotics is to shrink the surgeon, right? Make the surgeon on the scale of a few cells or so. And the idea then is that if you have a microsurgeon on this scale, what would you need it to do? Well, it would need to start investigating its environment. So, for example, it could detect chemical signals or poke certain cells and test how stiff they are. And then it would have to have an algorithm on board embedded in this computer chip that would tell it how to react based on what it's measuring. And so the idea then is that if you ever wanted to get 1 million or so robots moving across a surface, investigating it, responding to what they measure, you're going to have the brains on board. And that's really what this breakthrough in this technology is going to allow us to do. The brains of the robot, they're already available. What we did in this paper was we showed how to design a pair of legs that could integrate with such a brain. What we do is we fabricate a 7 nanometer thin layer of platinum, and then we cap it on one side with an inert material. When we apply a voltage to the platinum, that drives ions in the fluid that the robot is in to absorb onto the platinum surface. And as those ions absorb onto the surface, they bend the platinum. They cause forces that end up bending the platinum. And because they absorb on only one side and not the other side is capped by that inert material, then those forces are going to cause an asymmetry, which then creates a bend in a certain direction. So today, the way we do that was by putting photovoltaics that are essentially driving these platinum actuators. But in the future, when these computer chips are on board, you would shine light on the entire robot and tell the robot to go left or right or backwards, however you want. Developing the legs was indeed a major challenge, and that was done by our postdoc, Mark Miskin, who's now at UPenn as a faculty. But once you have the right materials, as Mark discovered them, then everything becomes easy because all the recipes are very standardized. It's the same kind of fabrication process that you use to make computer chips on a wafer, and every one of those computer chips is exactly the same. Now, the computer chips, that we've already known how to do. So, in fact, we just got back a wafer full of very primitive computer chips. The first one we call ClockBot. It has a signal, voltage signal that cycles every, some number of milliseconds. And the idea is that by accessing that signal at different phases of the cycle, you could first actuate the front legs, then actuate the back legs, and that we're doing today in the lab. So that chip is already, we've already shown that it works, and we're now integrating it with the legs. We have other robots. I think there's one called DogBot, which you can send signals via pulsed light, so like a Morse code, and tell it to go left, or tell it to go right. We're developing sheet-like robots where the sheet itself acts in a distributed way to deform and crawl up chemical gradients. These are all projects that we're pursuing today in the lab, and it's super fun and super exciting, as you can imagine.